Let's look at some examples using that expected value and standard deviation formula for working with discrete random variables. So I'm going to go ahead and write our formulas up at the top here, even though we can kind of get around these formulas, just kind of knowing the routine of how to solve for them. But with expected value, we want to add up, so that's our sigma symbol there. We want to add up our x values times their probabilities. And then for standard deviation, finding that average distance from the mean, what we're going to do is we'll have a big square root. So one square root at the end of our work. And what we're going to do is add up the squared deviations times their probabilities. So what we'll do is find those squared deviations, multiply with their probabilities, and add all those up, and then take a square root. And that symbol for mean right there, that's coming from our expected value. So whenever we calculate standard deviation, we have to find our expected value first. So we have this probability model right here where we have our x values, so our random outcomes in terms of number of repair calls within an hour. So this would be 0 calls, 1 call, 2 calls, 3 calls. And then what we're going to have is our probabilities. So the probability of getting no calls has a 10% chance, probability of getting 1 call in that hour is 30%, so on and so forth. Now, first thing we need to do is complete the table, so we don't know the probability that goes here. So the property that we want to use is that when you add up the probabilities, they should always add up to exactly 1. So to complete the table, what we're going to do for work is we'll take 1, take out the 0.1, take out the 0.3, take out the 0.4. So take out those probabilities that are already defined, and that'll give us what's left over, which is a 0.2. So now that works to all add up to exactly 1. All right, expected value, what we're going to do is use the formula. What it comes down to and how I think about it is, so we're multiplying our x values times their probabilities and adding them up. So what I think of is multiply, add, multiply, add, multiply, add, multiply. So we're reading across the table, multiplying those values, and then adding up in between. So I'm going to take that 0 times 0.1, plus 1 times 0.3, plus 2 times 0.4, plus 3 times 0.2. Then we put that in our calculator, and that should be a 1.7. So we could say is the shop can expect about 1 call, or sorry, that would round to a whole number of 2, so about 2 calls per hour. Again, for the sentence, round to what makes sense. If you wrote about just 1.7 calls per hour, absolutely correct. This is a math class, so if you provide the exact numbers, that's great. But you might feel more comfortable rounding to a whole number in certain cases, and in the sentence, you can absolutely do that. All right, there's our expected value. Now we need to find standard deviation. So we're going to go through this process of looking at our squared deviations, times their probabilities, and add those up. That'll give us our variance, and then we're going to take the square root. So how I like to organize it is I'm just going to look at our squared deviations, and I'm going to think about multiplying those with our probabilities. So squared deviations, we're going to take each x value minus the mean. So I'm going to take, in fact, let's see, there are 4 data points. You can even kind of arrange it and get the theme going here. So we're going to take each x value and minus the mean, which is 1.7. And then we're going to square those. So I'll get our squared deviations, and then what I'm going to do is multiply by their matching probability. So in our data value 0, we have a 0.1, then a 0.3, 0.4, 0.2. So we're fitting that structure there of squared deviation times probability. And then what I want to do is add those up. So this is where you'll want to go to a calculator like I showed in the last video. I was using the Desmos scientific calculator. GeoGebra also has one. But you want to write all of that out to add them up. And when you do that, that's going to give you variance. And in this case, that should come out to a 0.81. And then what we want to do is one step further and take the square root of that number, and that'll give us our standard deviation. So standard deviation, I'm going to take the square root of 0.81, which is a 0.9. So what I could say is the shop can expect about 2 calls per hour. I'm just going to go ahead and add to our sentence up there of taking that number and say, and on average, this will deviate by about and I'll just round that to a whole number of 1, so 1 call per hour. So there's mean and standard deviation. Probability questions, we'll just keep referring to that table. So what's the probability that they get 2 repair calls? So this is where we're looking for where does our variable equal to. So that'll happen when we have a probability of 0.4. So we'll just copy that value there, and then we could say there is a 40% chance they get 2 repair calls. At least. So we talked about this wording here. So probability of at least 1 repair call. So again, that's giving us our least value, and then we want everything larger. So this is the same thing as greater than or equal to. So what I'd want is the probability of x being greater than or equal to 1. So in terms of my table, what I'd want to include is starting at 1 and everything larger. And with that, we'll just add up those probabilities. So that'll be a 0.3 plus 0.4 plus 0.2, which is a 0.9. So there is a 90% chance. And then from there, they get at least 1 repair call. At most, so at most 2, this is saying our most value, and then everything smaller would be fine. So this is the equivalent of less than or equal to. So for notation, I would be looking at probability of x less than or equal to, and we're looking at 2 in this case. So for my table, what do I want? What I'd want to include is 2 and everything smaller. So I'd be adding up that 0.1, 0.3, and 0.4. Which will be a 0.8. So there is an 80% chance they get at most 2 repair calls. All right, this last one we didn't talk about in last video, but it's very important to notice the difference with these. So less than 2. So in that previous example, that was less than or equal to 2. With this example, we want strictly less than 2, which means we're no longer including 2. So if I go to my table, my area that I'm shading is a little different. It's not going to be going all the way to 2. Instead, what this would be the equivalent of is 0 and 1. To be strictly less than 2, we don't want to include 2, but we want to have everything up to 2. So in this case, what we could do is even write equivalent notation that this is the same thing as less than or equal to 1. That would be the same exact thing for these discrete cases where we have these specific outcomes. This doesn't work with a continuous number line, but with these discrete cases, we have these jumps of whole numbers. So you could have this equivalent notation, which can sometimes be helpful, but we'll be adding up that probability of 0, which was 0.1, plus that probability of 1, which was 0.3. So there is a 40% chance they get less than 2 repair calls, not class. All right. Let's look at this example where they don't give you the table and you actually have to set it up for yourself. So what we're going to do is we're going to roll a 6-sided die. If it comes up a 6, you win $100. If not, you get to roll again. If you get a 6 on the second time, you win $50. If not, you lose. So in terms of setting up our table, what I could do is go ahead and start with X and their probabilities. Now, when they describe the distribution, sometimes they'll tell you what you want X to represent. So probability distribution for the amount you win. So that's what X is going to represent here, the amount you win. So let's think about our different scenarios here. The case where we just roll a 6 on the first try, we're going to win $100. So that's one case. If not, you get to roll again. So on our second try, if we get a 6 on the second try, we're going to win $50. And if not, you lose, which means we don't get anything. So let me even write above this in words what this represents. This would just be the idea of rolling a 6. So in terms of probability, this just has a 1 out of 6 chance. And here you can either write the fraction, or if you want a rounded decimal, that would be fine too. I'm going to go ahead and do the rounded decimal. It'll be, as long as you round to 4 decimal places, it shouldn't be a huge difference in answers. I mean, the fraction's more accurate, but we kind of want to avoid fractions as much as we can. So that's just the probability of rolling a 6. That's coming from just 1 divided by 6. Now, with the $50, that's the case where we roll not a 6, and then a 6. So thinking about the probability here. And then that brought through our multiplication rule. And we just want to make sure we have independence here. With rolling a die, it's always a 1/6 chance. Each time you roll a die, the probabilities stay the same. So it's just going to be our straight multiplication rule. We don't need to worry about conditional at all. So rolling not a 6 and then a 6. So what we'd want is, what's the probability of not rolling a 6? Well, that would be the equivalent of saying rolling a 1, a 2, a 3, a 4, or a 5. So there's 5 possibilities out of 6. So that's our probability of not rolling a 6. And then probability of rolling a 6 is 1 out of 6. So we'd want to carry out that multiplication rule, which would be a 0.1389. And then our last case here is the idea of rolling not a 6 and then rolling not a 6 again. So with this calculation, similar to what we did in that last one, we're going to have multiplication rule because we're looking for this sequence of events, and we want not a 6, so there's 5 out of 6 possibilities for that, and then not a 6 again. So multiplying those, 0.6944. When you get to the end of these where you're setting up the distribution table for yourself, double check that it adds up to 1. Because if it's lower than 1, then either a probability was miscalculated or you're missing a scenario. All right, so we have our table there. I know there's a lot of extra work around it, but we really want to focus on our table for our calculations. So with that, expected value. So what we'll do is 100 times its probability plus 50 times its probability plus 0 times its probability. And if we add those up, that should come to a 23.615. So we could say is the expected winnings are about $23.62. Now, this is a spot, I kind of briefly mentioned it in the previous video, where students start to say, but that's not a possibility. If you play, you can't expect to win about $24 because it's not a possibility on our table. But this is the idea of long run behavior. So, and this is an idea that a lot of casinos use, is they set up a game, and yes, when you play once, these are the possibilities and those are the probabilities associated with it. But if they set up this game in the casino and have this idea of many, many people playing this game over and over and over, like sometimes they'll be paying out $100, sometimes they'll be paying out 50, and a lot of the time they'll be making money, so that's zero. But the idea is that of having a lot of people play the game, what do they expect in the long run? At the end of the day, what are they expecting people to leave the casino with in terms of money with this game? And the idea is that $23.62. So that's how it would average out over time. So we'll talk about that more with how the casinos kind of use this as a tool for figuring out how much to charge to play a game so that they're making money. So first, let's find our standard deviation. So let's set up our squared deviations times their probabilities. So I'm going to set up these three cases. We could have $100, $50, $0 minus the mean squared. And once we have those, then we want to multiply by their probabilities. So we have our probability of 0.1667, 0.1389, and 0.6944. And then what we'll do is add those up to get our variance, which should be 1,456.5818. And you don't need to write out the variance each time. There's just a few homework problems that ask you for variance, so I want to include it so you see the work. But this question's only asking for standard deviation, so if you're in the calculator and just want to add those up and take the square root right away, you don't need to write out the variance each time. But the standard deviation would be the square root of that number, which should be a 38.1652. So with this, the expected winnings, I'll just add this to the sentence up above there since it's already outlined. The expected winnings are about $23.62, and on average, this deviates by about $38.17. And this is also kind of a strange scenario where you are expecting a value that's less than how it varies. So like with this, expecting about $24, but then it's going to vary by $38 can seem kind of strange because it'll go into that realm of negative numbers. But this will happen when 0 is a likely outcome, which is exactly what we have here. That 0 outcome has a 69.44% chance of occurring. So when you have this kind of lower expected value, then standard deviation is typically because 0 is likely to happen. All right, so should you play this game if it costs $25? Why or why not? So with this, we expect to take home about $24, and they want to charge us $25 to play. So if we play this game all day, yes, we might win $100, we might win 50, but the long run expected winnings is about 24, which is less than the cost to play, and that is not good. So we would not want to play the game if it costs $25 because the cost of the game is higher than the expected winnings. With these types of questions, you could also think about profit, like what's the expected profit? So for formula for profit, you think about the difference between revenue and cost. So revenue is how much money you're making minus the cost of what you're doing. So in this case, if we did this, the revenue would be the $23.62. That's how much we expect to make, minus this cost that they're going to charge us of $25. So with this, we'd have this negative profit, which translates to a loss. We would expect this overall loss of $1.38. So you can use this profit formula. If it comes out positive, you're making money. If it comes out negative, you're losing money. So This setup here, if they charge $25 to play the game, this would be considered an unfair game. They're basically charging more than you're expecting to win, which this is something that casinos use. Yes, sometimes they have to pay out a lot of money, but they have formulas for how they're doing this to set it up so that in the long run, they're making money. So the idea of setting a cost for the game higher than the overall expected winnings in the long run. So if we wanted to set a cost of the game to make it fair, it would just be equal to the actual expected winnings. So we could just set it to $23.62. So in the long run, it would be breaking even. So this is something that happens with expected value, and it is a tool that's used out there in the real world.